Hey guys, Mr. Backerberg here. In this video, we're going to look at finding extreme values. Now, as we're looking at finding extreme values on a graph or of a function, there's a few places we're going to want to check. The interior domain points where a function is going to have local extreme values are going to be points where either the derivative of the function is equal to 0 or where the derivative of the function does not exist. But we also want to make sure that we're checking the endpoints of any given domain for potential extrema as well. Now, as we're looking at points on the interior of the domain of a function f, anywhere that derivative is equal to 0 or anywhere the derivative doesn't exist, like we just talked about, those are called critical points of the function f. And extreme values of a function can only happen at critical points of the function or at the endpoints of the function. Now, there are also these things called stationary points, and a point on the interior of the domain of our function f where the derivative of f is 0 is called a stationary point. And a stationary point can be either a minimum, a maximum, or it might be neither one. And the critical points and the stationary points of a function are not always the same. Now, if we want to look at finding extreme values on a closed interval from a to b, there's a few steps that we can follow. The first thing we want to do is find the critical numbers of the function f on the open interval from a to b. We're going to evaluate the function f at any of those critical numbers that we find on that interval from a to b. And then we're also going to evaluate the function at the endpoints a and b. Now, as we're comparing all of those different answers that we get from those critical numbers and from those endpoints, the smallest answer that we get out of all of those is the minimum value, and the biggest number that we find out of all of those is the maximum value. So taking a look at this example, we're going to try to find some absolute extrema. So we're going to find any absolute maximums and absolute minimums of the function f of x equals x to the 2/3 power on the closed interval from -2 to 3. Now, the first thing I'm going to do is find the derivative of this function. So, looking at what we've got, we're going to do a little power rule. So we'll drop down that 2/3 as a multiplier on the x. We're going to have to subtract 1 from the power. So if I take 2/3 and subtract 1, that's going to be -1/3 for my exponent. I don't typically like to deal with negative exponents, though, so I'm going to take that x to the -1/3 and put it on the bottom of my fraction in order to turn that power positive. But a 1/3 power is the same thing as a cube root of x. So we get 2/3 cube root of x. Now, there's two things we want to check for with this derivative. The first thing I'm going to do is see if there's any places where this derivative equals 0. So I'm going to take this 2/3 cube root of x and set it equal to 0. Now, if I was trying to solve this, I don't like fractions, so I would take that denominator and multiply it over to the other side. But if I take anything and multiply it by 0, I'm going to get 0. So then this will say 2 equals 0, which doesn't make any sense mathematically speaking. So there are no places where this derivative equals 0. The next thing I would look for is any places where the derivative doesn't exist. And since we're talking about a fraction, I would be concerned about 0 happening on the bottom of the fraction because you're never ever allowed to divide by 0. So as I'm looking at this, it would not be safe for me to plug 0 into this equation, because if I plug in 0 for x, do the cube root of 0, it's still 0, multiply that by 3, we get 0 in the denominator of the function. So this derivative does not exist at the x value of 0. So that's going to be a critical number for us. We're going to be testing out the x value of 0. But then we also want to test out the endpoints of our closed interval. So we're also going to test out the end value of -2, and we're also going to test out the end value of 3. So we're going to be plugging in those x values that we were just looking at, and we're plugging them into our original function. So I'm going to take 0 and store it as my x value. And then the function we were dealing with was x to the 2/3 power. So plugging in 0 there, we get 0 as our answer. The next value we're going to plug in is -2, so I'm going to take -2, store it as my x value, and then if I type out my function x to the 2/3 power, I get the decimal 1.59 approximately if we do a little rounding. And then our last value that we need to test out is 3, so I'm going to store 3 as an x value, and again type out my function x to the 2/3 power, and we get 2.08. Now we said that the largest of those answers that we got, that's our absolute maximum value. So this one right here where we just got about 2.08 using that x value of 3, that point is the absolute maximum on this interval from -2 to 3. Now the lowest point is the least of all of those answers that we got. So if we scroll up a little bit here to when we plugged in 0, when we plugged in 0, we got an answer of 0, and that was the lowest of our 3 answers. So the point 0, 0 is our absolute minimum. Now we can also check this graphically. So in my y equals, I've got the x to the 2/3 typed in. I will have to do a little bit of window adjusting. We wanted to look on the domain from -2 to 3. So I've adjusted my x min and my x max to reflect that. The x min is at -2, the x max is at 3. I also adjusted the y min and the y max just so we could get a pretty good picture of our graph. So now if I hit graph, the absolute maximum is the highest point that we can see anywhere on the graph, and it's happening at this right end value of 3, and we can see there that it's just a little bit above 2, because when we did it algebraically, we got 2.08. And then the absolute minimum is the lowest point on the graph, so we can see that that's happening right here at the origin, which is the point 0, 0. Now that other end point at -2, we tested it. It wasn't the highest, it wasn't the lowest, so that one wasn't an extreme value. It wasn't a maximum, and it wasn't a minimum. Now taking a look at this example, we're going to look at finding any extreme values for the function 1 over the square root of 4 minus x squared. Now we're not given a specified domain to look at for this function, but I want to think about what the domain of this function would actually be. And where I'm going to start first is by looking at that square root on the bottom of the fraction. We know that we're not allowed to square root negative numbers, so the stuff underneath the radical isn't allowed to be negative. So normally what we would do is we would take the 4 minus x squared, and in order to make sure that it's not going to be negative, we would say that this would have to be greater than or equal to 0. But I'm going to make one slight adjustment. Because this is on the bottom of a fraction, we know the bottom of the fraction is not allowed to be 0. So as we're finding the domain of this function, the stuff underneath the radical isn't actually allowed to be 0, since we can't have 0 on the bottom of that fraction. Now if we go through and solve this, I would subtract the 4 over to the right-hand side. So then we would have negative x squared is greater than -4. I would divide by -1, but when I do that, I have to remember to flip my inequality symbol around. So this is saying that I need my x squared values to be less than 4. Now, because this is a quadratic inequality, we have to be a little bit careful. Normally, we would think about square rooting both sides, and we'd have to remember to put a plus and a minus on that 2 when we square root the 4. But things get a little tricky because of that plus and that minus. The way this is going to work out, I'm actually going to take the -2 off of here, and I'm going to slide it to the left side of my inequality. And what this is going to say is that we need x values that are between -2 and +2. If we get anything smaller than -2, or if we get anything bigger than +2, then when we plug it into this function, we would end up with a negative number underneath the square root, which we're not allowed to do. So as we're looking at finding the extreme values for this function, we're going to use the implied domain for the function, which is x values that are between -2 and +2, but not including those end values, again, because it's not safe for the denominator of this fraction to be 0. But now we have to go through and actually find the derivative of this function. But the way the function is set up right now, It's not going to be real nice to find the derivative. Since it's a fraction, we would have to do the quotient rule, but I'm going to do a little rewriting with this to make finding the derivative easier. And the first thing I'm going to do is take that square root that's on the bottom and convert that over into a power. So this is going to be 4 minus x squared raised to the 1/2 power in the denominator. But then I'm going to swing that up to the top by using a negative exponent to get rid of the fraction. So then this is going to say 4 minus x squared to the negative 1/2 power. Now I haven't actually found the derivative yet. All I've done is rewritten this so that it's easier to do the derivative. Now if I do want to find the derivative of my function, because we've gotten rid of the fraction, now it's just going to be power rule combined with chain rule. So I'm going to drop that negative 1/2 power down. I'm going to leave the 4 minus x squared alone, subtract 1 from the power, and that's going to be negative 3/2. But then because of this inside stuff with our parentheses, we also have to do the chain rule. So the derivative of the inside, well, the derivative of 4 is just 0. And if we do the power rule with this negative x squared, I would have to drop the 2 down, so that becomes negative 2x, subtract 1 from the power, and that ends up just being to the first power. Now I do want to clean this derivative up just a little bit since it has that negative exponent in there. I'm going to drop that down to the bottom of our fraction with our 2. So this is going to be 2 times 4 minus x squared to the 3/2 power. And on top, we've got this negative 1, but we've also got this negative 2x. So that double negative is going to turn this into positive 2x. But then because we have the 2 on top and the 2 on bottom, we're going to be able to cancel those out. So the derivative of this function is going to be x over 4 minus x squared being raised to the 3/2 power. Now as far as finding the critical numbers for this function, the first thing we want to do is check where the derivative is equal to 0. So I'm going to take this derivative that we just got and set it equal to 0. So x over 4 minus x squared to the 3/2 power is equal to 0. If I multiply that denominator over to the other side to that 0, I just get x equals 0. So we've got a critical number at the x value of 0. Now normally we would say that we're going to test the endpoints of our interval as well, but because we've got an open interval where we're infinitely getting closer to -2 and infinitely getting closer to +2, it doesn't really have any endpoints since we can keep getting closer and closer to those values. So the only critical number that we've got to test in our function is 0. So if we go back to our original function and plug in 0, well, 0 squared is 0, 4 minus 0 is 4, and the square root of 4 is 2. So if we plug in the x value of 0, then f of 0 is 1/2. Now we said before, if we have multiple critical numbers that we're testing, the biggest one is the maximum and the lowest one is the minimum. Well, here we've only got one critical number, so it's a little difficult for us to tell if this is going to be a maximum value or a minimum value. So looking at the graph is going to give us the best idea of what's happening here. So in my y equals screen, I typed in that function. I did adjust my window just a little bit. We had an implied domain between -2 and +2. So for my x min and my x max, I went just a little bit outside of that. For my y min and my y max, I'm going from -1 to 3. If I hit graph, I get a picture that looks like this, kind of this bowl shape. So we were looking at that x value of 0, and we can see that that's at the bottom of our curve. So that must be a minimum point. Taking a look at this example, we're going to be finding some extreme values. So we want to find the extreme values of the piecewise function f of x equals 5 minus 2x squared for x values that are less than or equal to 1, and then x plus 2 for x values that are greater than 1. Now I actually want to look at this one graphically first because it can give us some clues as to what's going to happen as we look at finding the extreme values algebraically. So in my y equals screen, I've got both pieces of that piecewise defined function typed in over their specified domains that we were given. When I hit graph, we're going to get a picture that looks something like this. So that part of a parabola is the first piece of our function for x values that are less than or equal to 1, and then that line is the second piece of our function for x values that were greater than 1. Now, looking at extreme values, maxes and mins, we can see on the blue portion of our graph, there's this rounded piece where it comes to a peak up at the top. That looks like that's happening at the x value of 0, and it looks like the y value is maybe 5 in there. So we're going to guess that maybe we've got a local maximum happening at 0, 5, and we'll see if we can algebraically prove that later. Now over here, where we've got these two pieces of the graph coming together, it looks like they're disconnected, but they do actually come to that y value of 3 in there. Now the derivative there doesn't actually exist, which is going to lead us towards another critical point, and it looks like that's potentially happening at 1, 3, so we would call that a relative minimum. But again, we're going to see if we can algebraically prove that as well. So as we're looking at this piecewise function, and we're finding those extreme values, we want to find the derivatives. So if I look at the first piece and do its derivative, well, if I differentiate the 5, that's just going to turn into 0. If I do the power rule with the second piece, drop that 2 down as a multiplier to the negative 2, and I'll get negative 4x. Subtract 1 from the power, and it's just to the first power. Now, if I do the derivative of that second piece of our function, the x plus 2, well, differentiating the x just turns into 1, and differentiating the 2 turns into 0. So these are our two separate derivatives. Now, one way that we find critical points is by setting them equal to 0. So if I start with this first one with the negative 4x and set it equal to 0, then I'll get a critical number at the x value of 0. Now, if I want to figure out the y value for that point, we have to pay attention to our domains. I can't plug that into the second piece because my function isn't defined at 0 there, but my function is defined at the x value of 0 for that first piece. So if I plug 0 into that first piece of my piecewise function, I'll end up getting a y value, f of 0 is going to be 5. Now, I'm not going to worry about setting the 1 equal to 0. That wouldn't mathematically make any sense for us to do, since 1 can't equal 0. So we're not going to get any critical points from that second piece of our function. Now, we also said that the derivative wasn't going to exist at 1. There was something weird happening at the x value of 1. And the way we're going to have to approach this, because we're dealing with a piecewise function, is we're going to have to look at the left and right hand derivatives. And in order for the derivative to exist, when we do the left and the right hand derivative, they would have to have the same values. So what we're going to end up showing is that they have different values, and therefore that the derivative doesn't exist at that x value of 1. That's what's going to make 1 be a critical number. And then once we know that 1 is a critical number, then we'll be able to test it out to see what that point would be on the graph. Now, to do our one-sided derivatives, we're going to have to do the limit definition of a derivative. So we're going to do the limit as h approaches 0 of f of x plus h minus f of x all over h. But we're doing one-sided derivatives. So for this first one, I'm going to look as h is approaching 0 from the right-hand side. Now, we also want to remember that we're trying to test out what's happening at an x value of 1. So I can rewrite this with that 1 plugged in for x. So then this is going to be f of 1 plus h minus f of 1 all over h. And we're still doing this limit as h approaches 0 from the right-hand side. I'm going to scroll up real quick here. We're approaching 1, and we're doing a right-hand derivative here. So as we're approaching 1 from the right-hand side, we're going to have to use this bottom piece of our function, that x plus 2. So if I'm doing f of 1 plus h and using the function x plus 2, I'm going to replace the x with 1 plus h, but then I've still got that plus 2 in there. And then on the back end, doing f of 1, if I plug 1 into the x plus 2, then I just get 3 as my answer. And this is all over h. And again, we're doing this limit as h is approaching 0 from the right-hand side. Now, if I look at combining the 1, the 2, and the negative 3, those are all just going to cancel each other out. So I get h over h And h over h just divides out into 1. So this one-sided derivative from the right-hand side equals 1. Now I'm also going to do the one-sided derivative, but approaching from the left-hand side. So I'm going to do the limit of f of x plus h minus f of x all over h, but this time we're going to approach 0 from the left-hand side. And again, we want to remember that we're using an x value of 1, so I'm going to fill that in for the x's in here. So f of 1 plus h minus f of 1 all over h, and again doing this limit as h approaches 0 from the left-hand side. Now, since we're approaching 1 from the left-hand side, we're going to have to use this top piece of our function, this 5 minus 2x squared, and we're going to be filling in the 1 plus h and also just filling in the 1. So then this is going to say the limit as h approaches 0 from the left-hand side. Now, plugging in the 1 plus h, then we're going to get 5 minus 2 times 1 plus h squared minus, now if I just plug in the 1, we're going to end up getting 3, and this is all going to be over h. We're going to work on simplifying this down. So this is going to say 5 minus 2 times, now squaring this 1 plus h means that we're going to be multiplying it by itself. So we're going to have to FOIL all that out. If we do that, we're going to get 1 plus 2h plus h squared, and then this will still have the minus 3 on the back end, and this is all over h. We're going to have to distribute this negative 2 through here. So this is going to say 5 minus 2 minus 4h minus 2h squared minus 3. And this is all still over h. Looking at combining like terms, I see this 5, this negative 2, and this negative 3. Those are all going to cancel each other out. So I get negative 4h minus 2h squared all over h. And I guess we want to remember that we're still doing this limit as h approaches 0 from the left-hand side. It's still not safe for me to plug in 0 because I've got that h on the bottom of my fraction. So what I can do is take out a GCF on top of 2h. And if I do that, this is going to be negative 2 minus 2h. And this is all still over h. We can cancel these h's out. So we get 2 times negative 2 minus 2h. Plug in the 0 for my h, and this back end term just turns into 0. 2 times the negative 2 that's left over gives me negative 4. So when we did the right-hand limit, we got 1. When we did the left-hand limit, we got negative 4. So because those limits are different, then the derivative doesn't actually exist at the x value of 1. That's what we were trying to prove. Showing that the derivative doesn't exist means that x equals 1 is going to give us a critical point on our graph. So then we want to figure out what the y value would be if we plugged in 1. Now, as we're looking at our piecewise function, it's safe to plug in 1 to the top piece. So 1 squared is 1, times 2 is 2, and 5 minus 2 is 3. So we would say that f of 1 is 3. So far we've come up with the points 0, 5, and 1, 3. We don't have to worry about the endpoints of our domain because this function is defined for all x values from negative infinity to positive infinity, so it really doesn't have any endpoints. So these are our only two critical points that we're worried about. Because this point 0, 5 has the biggest y value, it's the maximum point, and because this 1, 3 has the lowest y value, it's the minimum point. In this last example, we're going to look at finding extreme values using graphical methods. So we're going to find the extreme values of the function natural log of the absolute value of x over 1 plus x squared. Now, before we get to the actual graph, I want to talk about the domain of this function. We're dealing with a natural log, and anytime you're dealing with logarithms, you can't do the logarithm of a negative number, and you also can't do a logarithm of 0. Well, we don't have to worry about negative numbers because we've got these absolute value bars around here. So even if we get a negative value from that fraction, the absolute value bars will turn it into a positive value. So negatives aren't an issue, but 0 would be an issue. And the x value that we're going to have to worry about is we're not going to be allowed to use the x value of 0, because if we plug the 0 in, we'd get 0 on the top of the fraction, and 0 divided by 1 would be 0. So 0 needs to be excluded from the domain, and that's the only value that needs to be excluded. Now in my calculator, I've got that function typed in, so I'm going to hit graph. Now on this graph, it doesn't quite show it all the way. There's technically a vertical asymptote happening at 0, so these ends of the graph should keep extending down forever and ever following that vertical asymptote, and that'll affect things as we're talking about maximums and minimums. Now what I see as we're looking at maybe finding maximum values on this graph, I see that on the left-hand side my graph starts increasing, but then eventually it turns and starts going down. So somewhere in here there's going to have to be a maximum point, and something similar is happening on the right-hand side. We've got this downward shape on either side, so there has to be a highest point in here somewhere. So to find those maximum points, I'm going to do second calc and pick option number 4. That's my maximum. It asks me for a left bound point, so that means something on the left side of where we think the maximum is happening. So I'm just going to arrow over here, hit enter. Then I'm going to arrow to the right because it asked me for a right bound point. So I want to go to another point that's lower than where we think the maximum is happening. Hit enter. We can take a guess, but we don't have to. We can just hit enter one more time. So this is telling me that I've got a maximum point at the x value of -1. If we round that off, and its y value there is -0.69 if we round that off. Now if we find the maximum point on the right hand side as well, so I'm going to arrow over here, it asks for a left bound point, so I want to be on the left side of where I think that maximum is happening. I'll hit enter, then I'll arrow over to the right past where I think the maximum is happening, enter 2 more times, and this time we get a maximum value. Now if I round this x value off, it's going to be at +1, and this is going to have a y value again of -0.69. Now as far as a local minimum, these ends of the graph would continue out forever and ever, and they would keep going down. So we're not going to have any minimums there since those would keep going down. And then in the middle here, where we've got this vertical asymptote where I said our graph would keep going down forever and ever following that vertical asymptote, it's going to keep extending down forever, so we're never going to hit a bottom value, so there's not going to be any local minimums there either. Now one last thing that I want to talk about real quick is that critical numbers and endpoints don't always signal an extreme value. If we look at the function y equals x cubed, if we do its derivative, that's going to be 3x squared. One way to find critical numbers is by figuring out where the derivative is equal to 0. So if I take this 3x squared and set it equal to 0, divide the 3 over, and I get x squared equals 0, square root both sides, so we've got a critical number happening at 0. But if we think about what a cubic graph looks like, our graph is going to look something like this. So at the x value of 0, that's not a high point, so it's not a maximum. It's also not a low point, so it's not a minimum. So even though we've got a critical number at the x value of 0, it's not a maximum and it's not a minimum either. That's going to be it for this video. Thanks for watching.